Dear Professor Yao and dear Pranava and Colin, my topic is jamming of ground flow through constrictions and its application in AM. Actually, jamming is a very old topic. For example, in a hopper flow, when the outlet size is very narrow, if the particles are discharged from the hopper, after some time, for example, 10 minutes or 1 minute or 10 seconds, the particles would be jammed here, and then no particle flow anymore. Of course, in other systems, for example, such as particle flow, confined flow, and also shift through bottlenecks, this also jamming. Of course, in some articles or some researchers, jamming sometimes is also replaced by the word arching or clocking. And there's also a lot of jamming in shear flow. For jamming in shear flow, it usually means that the particle and under the effect of shearing, the particle system will change from unjammed to unjammed and then flow. The group of Brihinger and also Ludin did a lot of work on this topic, and they are works very nice. For example, Brihinger developed a jamming map, including a shear jammed and a fragile jammed state. And Ludin thinks the jam point or the particle fraction and the transition point is not constant, and the critical particle fraction is affected by the particle friction and also other factors. Of course, there are many articles on the topic, especially on the jamming and shear flow, and there are more details can be referred to this review paper. It's a very new review paper, very wonderful. So in these systems, for example, in hot flow, the walls are static, low moving, and in the shear flow, actually there's no constrictions, means that there's low outlets or low very bottlenecks. So there's a question for this kind of systems. For example, in this kind of system, there's a moving blade. Here's the particles through a large gap size onto a rock plate. So there's a shear blade, and there's also a bottlenecks. And in these systems, a rotating blade moves downward and also rotates. So in this system, there's also a very gap size and also the shearing effect from the blade. So this kind of systems is much different to the shear flow, the traditional shear flow and the traditional hot flow. So I think in this kind of systems, the jamming is much different to the jamming in hot flow and in shear flow. Okay, so I first show some result on the jamming in FT4 rhometer. So this is a snapshot of the FT4 rhometer, and also Colin also mentioned it. This is a blade rotates and also moves downward. Okay, the gap between the blade tip and the base wall is very small. So in this work, I do two tests. Use the DM simulation. The downward test. In the downward test, the blade rotates anticlockwise and also move downwards. So in this test, the particles in high stress flow. And in the upward test, the particles, the blade rotates clockwise and then move upward. So in this test, the particles is in low stress flow. And in FT4 rhometer, we usually use the work done by the blade to quantify the flowability of the powder. So it means that if the blade is very large energy to start the particle bed, means that the flow energy also is very large. usually indicates that the powder is very difficult to flow. So we here when the particles is glass bit and the diameter of the vessel is 25 millimeters. So the gap between the blade tip and the vessel is only 0.75 millimeters. We here I do the three cases: case A, case B, and case C. For case A, the powder, the Young's modulus, and the surface energy is the standard value and measured from the experiment. And in case B and case C, the Young's modulus is scaled down. But the scale law is different. In case B, we use the bond number to scale down the Young's modulus, to scale down the surface energy. In case C, we use the coefficient number to scale down the surface energy. So here the bond number is the ratio of the maximum of force to the particle weight. And the coefficient number is the maximum coefficient work to the work done by the particle weight. So in the general theory, we usually think that the flowability can be inferred by the bond number or coefficient number. So in these cases, the flowability of the powder in case A should be has the same value as case B or case C. So it means that the flow energy of powder in case A should have the same value as that of case B or case C. These are some results of the simulation. These are downward tests. The blade rotates like this and also moves downward. So we can see that in case A, the force and torque, there are a lot of peaks, and the peaks is very, very large, much larger than the maximum value in case B and case C. For example, in case B and case C, the maximum value is only 2 Newton, but here it can be even to 50 Newton or negative 70 Newton. Yeah, very, very large. And this is also the same situation of the torque. Yeah, and we can see here, actually the force is very disorderly. It can be positive and also can be negative. Yeah. So we can think here that when there's a peak, the jamming occurs. Yeah. So the jamming can induce very large force on the blade. So there's a very strong jamming, mechanical jamming. And the upward tilt, the blade moves upward and also rotates. So this is the same case for case A. The force and torque is very large. There are many peaks. Yeah. For case B and case C, it is okay. Yeah. So we also use the flow energy because in FT4 we usually use the flow energy to quantify the flowability of the powder. So as in previous page, we think that the powder in case A should have the same flow energy or the same flow energy as that of case B or case C. But here you can find that in case A, the flow energy, the flow energy is the integration of the force and torque. The flow energy in case A is much larger than that in case B or case C. And you can find here that the flow energy increase in a stepwise style, like stairs, like stairs, So the stairs means is caused by the jamming because the jamming is not stable. It can occur and then disappear and then occurs again. So when the jamming occurs, the flow energy increase suddenly and then flatted and then increase again. For the flow energy in the case B and case C is very normal. Very good, very normal. But in case A, the flow energy is too large. It can be even 10 times or 30 times larger. So we can think that in the raw meter, in the FTO raw meter, if there's jamming, flow energy could not represent the flowability of the bulk particles anymore. We also check the jump structure. Here we can find that the jumped particles are almost all located in the gap between the relative and the phase wall. Yeah, jump almost all in this region. Yeah, but the exact locations is random. It can be between the middle. It can also be the edge. Yeah. And we also calculate the number, the total number of jumped particles, and then get this plot. Yeah, this plot. We can find that the number of the jumped particles is also not fixed. It can be one particle. It can also be even to 6 particles. Yeah. Of course, the jump structure with only one jumped particles has a large probability. And we also track the generation of the jamming and also the disappearance of the jamming. We can find that the jump particles, yeah, this is the from given time, yeah, this is the formation of the jamming, and also the disappearance of the jamming. We can find that the jump particles is almost, yeah, squeezed into and out of the gap. Yeah, this for both the downward test and upward test. Here is also the same situation. Yeah, like this. Yeah, the purple, the particle in purple color is a jumped particle. And when the jamming occurs, there's a very strong force chain, like here, force chain, yeah, correlating their jumped particles to the blade tip and also to the phase wall. But the force chain would disappear if the jamming disappears. Yeah. And we also do some analysis on the survival time of the jamming, because jamming here is not stable. It can occurs and then kept for a short time and then disappear, and then after some time it can occur again. So here we plot the maximum compressed force of all particles, get the maximum value, and then plot it with time. So we think if the dead point, if the continuous dead points with force larger than the critical value, we think all the time steps belong to the same event. So from this point to this point, the jamming event survives, or the jamming is kept. But after this time, the jamming disappears, and this time again, the jamming occurs again. Yeah, like this. Yeah, occurs and then kept, and then disappear, and then occurs again, and then disappear again. So from this plot, we get the start point and also the end point of the jamming event, and then we can get the duration of the jamming event, and I can also get the frequency of the jamming event. We can find that here the frequency of the jamming event decreased sharply with its survival time, yeah, the survival time, and also the total frequency of the jamming event is in a low frequency, less than 50 Hertz. And the jamming event with duration in 0.01 second to 0.02 seconds has a large probability. So the jamming event is in very low frequency. So that's why if we use the force sensor of the FT meter, we cannot observe it, because the FT meter, the force and torque is saved only per 0.04 seconds. But here we can find the jamming event, the duration of the jamming event is usually less than this value. We also, because we in FT4 raw meter, we also do some experiment use very large particles. But if we, in that case, I heard very large, very loud noise, so we cannot do experiment because it may damage the FT4 raw meter. But we use some smaller particles, for example, glass bead and also P particles. The particle size is smaller than the ones in the simulation. We can find here. After some tests, the surface of the particles are damaged. There are several pits, pits and scratches can be found on the surface. And for P particles, there are also some very long, like this, very long scratch, and also some patches can be observed on the surface. So this particle surface damage can also indicate that particle jamming occurs in the gap. So the jamming would lead to a large force between the particle and the blade tip, and then a small quantity of the material is stuffed out from the particle surface by the blade tip. Okay, this is some experiment, and we can from the information of simulation and experiment we can get these conclusions. And this one very important conclusion is that if the gap is larger than 2 and 0.5 d90 for the particle sample with small particle size, the jamming can be avoided. Or for the powder, when the gap is much less than 1 d90, then D10 for the powder sample with large particles, the jamming can also be avoided. So the gap, if we want to avoid the jamming, the gap should be larger than 2 and 5 d90 or less than 210. Okay, this is jamming in FT4 raw meter. Now I move to the second topic, the jamming in blade spacing system. In this work, I do some experiment. The experiment is like this. Yeah, it's like a moving blade, and move upwards, and then spread the powder onto the rough base. Here we use a lot of filler gauge to control the gap size. Yeah, because the gap size here is very narrow. It's very narrow between the blade tip and also the rough base. In the experiment, we measure the force on the base. Yeah, well, there's a force sensor underneath the base, and we also take some pictures of the spread layer when the experiment is finished. We use 3 kinds of material. In case powder A is steel powder, and its shape is very spherical. And powder B and powder C is sand powder, and its particle shape is angular. For powder C, it is the sand powder coated by binder. So we can find here, in case A, the flowability is very good, but for case C, the flowability is very worse. It's very worse. And this experiment result. These are force on the base we can find here. For different kinds of powder, if the gap is very narrow, in the distance between the blade tip and the base, when the gap size is very narrow, there's a lot of peaks, the same as the simulation in FT4. Yeah, but when the gap is large, there's low force peaks. So we think the peaks describe the occurs of jamming. So if there's a peak, the jamming occurs. the low peak, low jamming. And you can find here, jamming is not stable, it's transient, and in dynamic state, it is much different to the jamming in hop flow. Because in hop flow, the jamming, when the jamming occurs, there's no particle flow anymore. The jamming exists forever. But in the blast-veiling system, the jamming is transient. It can occur and then disappears and then occurs again. And we also can find here, when the gap size is larger than 2 and 0.1, the jamming will disappear. For example, the mechanical jamming would disappear. So we use the same method as FT4. We can get some information of the jamming event. We also plot the force with time, and then we use a critical value of 30 micronewton. For example, if the force is larger than the critical value, we think the jamming occurs. So the jamming starts at this point and then exists and survives. And at this point, the jamming disappears. After some time, the jamming occurs again and then disappear again and then occurs, disappear. We can also get the start point and the end point of the jamming event, and then we get the duration. And we use the area, the force, and the time. The area are the strengths of the jamming. We do some experiment and then do some average. So this is the duration of the jamming event with the gap height. Yeah, we can find here. This is the strength of with the gap height. We can find here for powder B, the duration, strength, and also force is the largest, and then is the powder A. For powder C, the duration and strength is the smallest. So we can think that for mechanical jamming, as described by the force, the powder B is larger than the powder A. So angular particles are more prone to jamming than the sphere particles. So the factors affecting the mechanical jamming is gap height, and then the particle shape, and then cohesion. Besides the mechanical jamming are described by the force, we also do some analysis on the empty patches. So we take some pictures of the sphere layer. So the empty patches, it means that the base plate not covered by the particles. For example, like here. Here is these are empty patches, no particles covered on the base. So we use the raw picture and then make binary and then get the empty patches by the user software of IMFTF. This is the area of the empty patches. Yeah, empty patches. We can find here port C larger than port B, larger than port A. So here, so based on this information, we think not all empty patches are induced by the mechanical jamming. There's a lot of kind of jamming, cohesion-induced jamming. So if the part is very cohesive, there's also jamming around the gap region, but the jamming is not very strong. Okay? It's not very strong, but you can also induce some defects on the layer. So let's record the jamming in hop flow. In hop flow, the critical gap size is usually 5 to 6 particle diameter. But here, in the blast-veiling system, the critical gap size for mechanical jamming is usually 2 to 2.5 D90. So the reason I think is that in hop flow, both two walls are static, but in spinning system, there's only the base wall is static. So the critical gap size is also half of the ones in hop flow. And there's a lot of features is that in the whole flow, all particles are jammed, but in the jamming in the spinning particle spinning system, only some particles are jammed. So the jamming is local. Not all particles, not all particles jammed. Only the particles close to the plate tip is jammed. And we also draw a regime map for jamming. The jam here, because I think there are many factors is the gap size. So this gap size and this increase of the interlocking or more cohesive. So if the particles are not cohesive, and also when the gap size less than the critical value, then mechanical jamming will occur. But if the particles are very cohesive, it can induce cohesion-induced jamming, or even slug flow. For example, like here, low particles, all particles moved with the blade, and low particles fed onto the base. So this like the full slip or slug flow. Even in this case, the base is also rough, or the powder is very too cohesive, so it can induce the slug flow. And between the mechanical jamming and the cohesion jamming, there's a combined jamming. Both kind of jamming occurs. So there's a very important parameter is the critical gap size. The critical gap size increase with the interlocking or increase with the particle shape. So it means that if the particles are very angular, the jamming can also occur and a very large gap size. Also, if the particles are very cohesive, the jamming can also occur and very large gap size. For example, it can even occur and when the gap size is 3 times D90 or 4 times D90. Okay, these are some conclusions of the jamming in our spinning flow. And here the main conclusion is that the critical size. The critical size for mechanical jamming and depends on the particle properties, for example, such as the particle shape or the particle cohesion. Okay, I now move to the third part or the last part, the application of jamming in AM. So the first application is the application of jamming in 3D printing, the SLM or binder gelatin printing. From this result and also from this both simulation and also experiment, you can find that the defects or the empty parties defects correlate well with the force on the base. So if there's jamming occurs, for example, like there's a very large peaks, there's also empty parties here, correlate very well. So I also do some summarize of empty parties in the industry or in the machine. You can find that most defects in the split layer in AM is due to particle jamming, like the rifts or ridges or graphs, or like this, or can be linked to the particle jamming. So the jamming detection and how to avoid the jamming is very important for the real machine. And in the possibility EM, sometimes the blade may be weird. In all that, we usually think the spade wear is due to the protruding of the blade against to the base. But here we can show that the blade wear can also due to jamming. So it means that even the gap is larger than the particle size. Once there's jamming, the blade will be weird. So the wear depth of the blade increase spillway like stairs. If there's jamming, the blade will be weird. No jamming, no wear. So there's a very new mechanism for blade wear in AM. due to particle jamming. And we also, based on this information, we also give the industry this as a suggestion. For example, like the blade, the edge, the after side of the blade, use an angle. Yeah, if you use this blade, the wear is much less than without modification. Yeah, the wear is very small. But in this the second case, if the blade is normal, yeah, there's a very large wear. And we also think that for in the post fading in because sometimes the industry or the researchers think the severability of powder is same as the flowability. But from here we think that the particle jamming makes the severity different from the flowability. So the severity is different from the flowability. There are different things. Of course, sometimes they have some relationships. There are different things because due to particle jamming. And the second application is and is the additive friction stir deposition. This is a very new kind of 3D printing. In this method, there's a tool rotate and very fast speed, and then it can stir and flick against with the layer. So and the effect of the heat due to friction and also the force due to the tool, the materials can be deposited onto the base layer by layer. So here, my focus is mainly the powder-based FSD. So in this case here, we use a screw to feed the powder into the gap, and then let the tool rotates the powder and also stir the powder and also compress the powder, and then make the powder deposit onto the base to form a solid part. So actually, this new method is very challenging because we usually find that the powder is jumped here. If the powder is jumped here, then the painting will be stopped, and this slow the painting can't continue because if the powder is jumped, it's very difficult to continue. I do some experiment like this. Yeah, this is a screw. As the powder is fed into the screw, and then screw will test and feed the powder onto the base. You can find here, there's some pictures of the jamming. Yeah, in this case, the particles are jammed, and the outlet of the funnel. Yeah, and the jamming is very solid. It can be in the experiment we will use a metal rod to dig out it. Yeah, and here these are large particles. This is fine powder. If we use fine powder, the jamming also occurs, and the powder there's very large heat. A large heat generated due to jamming, and then some powder is even solidated. And the main problem of jamming is that if jamming occurs, the motor will be stopped. Because jamming will generate a very large force on the motor, and the motor cannot work anymore. And we also use because in the machine we want to avoid the jamming. So here we use two mass flow rate. The first one is the maximum flow rate through the screw. This is the maximum, yeah, not the real value, yeah, because the real flow rate is affected by many factors such as the pitch or the powder properties. And the second flow rate is the mass flow rate through the gap here, just through the here, and through this gap to here. Yeah. This equation is adopted from my previous work on the blast gradient. So we use a ratio. Use this one divided by this one. Use the ratio to quantify the occur or not occur of the jamming. We can find here. If the ratio is larger than 5, the jamming will occur. Yeah. If the RF is less than this value, the jamming will not occur. So use the information of this. We can do some work on the printing, on the part of printing. Yeah. If we don't know this information, the jamming will occur like this. For example, this strong jamming and the printing can't be continued. But if we control the speed of the screw based on the information of jamming, we can let the printing continue like this. Yeah, this is the manufactured part. So the avoid jamming and also the well controlling of the screw feeding rate is very important for FSD. Okay, actually jamming is very old topic as developed from Professor Behinger, but it has new life in both the traditional laser sintering melting or the binding manufacturing, and it also in the newly developed FSD, there's also jamming. And my research topic actually is from single particle through experiment and also DM simulation to the bulk particle flow, and then use the information to do some applications in industry. And thank you very much to my workers. It's really the group of Martaba. Thank you.
Yes, thanks a lot for Professor Lance there. Excellent talk. Yes, very good. And you give us particle jumping. Actually, I first realized this words. Yes, previously I don't know actually. Yes, very, very interesting work. Yeah. Now, so I asked some questions here. I will one by one ask you. Yeah. And one from actually from Majtaba, from Kadiri. Yeah. Is ASDF an established method? It seems to be too complicated. There are two competing rates of delivery in series. Yeah, Professor Lion. Can you please answer? You can also.
Yes. The FSD is very complicated. It's very complicated. It's very for powder. Actually, in low body, fit this work. Use the powder to because in FSD, people usually use a rod, a solid rod. I can show the point.
So what type of powder is this developed for now?
This one, yeah. Actually for this method, if we use a solid rod is very easy because solid rod is a solid, so it can be pushed down and then rotated. But for powder, it can flow. It is discrete, so it's very difficult to push it down. If you push too large, the jamming will occur. If you not push the powder down, the powder cannot flow into the gap. Yeah, so this is very difficult because the powder is much different to the solid rod.
So what particle size this is best for?
I don't know.
No. Right.
So in my experiment, I use the powder size of 1 millimeters. 1 millimeters. but some guys use a particle size of 5 millimeters. Okay, so about actually low body public papers on this topic actually. It is very new.
Yeah. Okay. May I ask a follow-up question, June?
Yeah.
So when you compare the transient jamming in spreading to jamming in hoppers, and you say that the mechanism is different, I'm not sure whether the underlying contact mechanics operating in these two systems is very different, because in a way in hopper, of course, when you have complete jamming, then you have arching, but before you get to that, you get also some transient jamming, force change, not at the sort of outlet, but higher up you get a little bit of contacts which are sustained for a very brief moment and collapse. So in a way, the underlying mechanism of jamming, maybe the comparison is not really helpful. But then the other thing which comes to my mind is that in industrial practice, Nan, I've come across cases where the gap of the spreader blade is comparable or even smaller than D90 by number. And based on your work, I have been always surprised why they are using such narrow gap. But that is the case. So you get constant jamming, I suppose, in industrial practice. Can you give some thoughts on your experience on the industrial side?
Actually, because I want to do some more on jamming, so that's why I use very small, larger gap size.
Mm-hmm.
Yeah.
Okay.
Because only under this gap size, the jamming can be observed.
Yeah, but actually, what you say about the segregation occurring as a function of gap size and also this spreader or the roller speed, that one I have seen it in industrial practice. So in a way, your findings, your predictions have come to fruition there. Yeah, thank you very much. Very nice talk.
Yeah.
Okay, Kadri, are you happy with his answer? Is okay?
Yes. Thank you. Yes.
Yeah. So Colin actually have some question here. How did you determine the flow rate ratio threshold of 5.0 separates jumping and no jumping cases? His first question.
Okay. For the first question, here I only use the data point. Yeah. The data point. So this value mainly comes from the data point, because we can use a line to feed in the data. Feeding the data. Yeah.
Okay. Yeah, that makes sense.
Okay.
Okay. The Colin's second question is for the AFSD. I assume you also need to move the tool laterally across the width of the bed as well.
Yes, of course. But in the experiment, I don't do this. I just only laser. Okay, like here. Only let the tool moves forwards, only forwards. Yeah, like this, only forwards, one direction. So the screw rotates, and then the system moves forwards.
Yeah.
And because if we translate in two directions, it's too complex.
Yeah. I guess this follows up from Mustaba's point that comparing to a spreader tool that is spreading across the whole width at once, you'd need to move this one a lot faster because you're having to go across as you progress forward. So you'd need to be able to deliver at higher speed to still be have the same rate of production.
Yeah.
Okay. Colin, do you finish your questions?
I have, yes.
Yes, thank you. So I also have some question. I'm very interested in your talk actually. For your first section, and do you have some? You show some particle, actually some particle breakage, yeah, some piece on the particles the surface, yeah.
Yeah,
the jumping. Yeah. You get some pictures actually.
Yeah.
Do you have some more work? The application of the jumping, you just show your you use your jumping to decrease the wear. Yeah, I'm thinking it's very good. Yes, but you speak it very quickly. Can you please give me the details of this work?
Okay. So
Yeah. Right. Yeah. You see the lab.
Yeah.
Can you give us more details about the story?
So actually sometimes we the researchers in the industry usually think the wear is due to the blade protrude the base. But here you can find that the spider can also be weared by the jamming. So, for example, if there's jamming, there's a very large force on between the particles and the blade, and then blade will be weared. So, for example, if there's a jamming, yeah, the wear increase suddenly. Yeah, if there's no jamming, no wear, this jamming wear will be like this. This is not different.
How do you change this status of jumping of the particles during your processing, during your work?
Yeah,
how do you control this?
Use the force on the base.
The force on the base.
And also we can also get some jump structures. For example, here, the particles jump here. Yeah.
I mean, how do you change it and how do you modify it? Yeah.
Modify just like the blade, the edge. Yeah, modify the profile of the bottom of the blade. Yeah,
modify
this. The profile of the blade bottom. Yeah. For example, the blade is usually like this. Yeah. Flatted. But here we can like this. Yeah. Use a very small angle. Yeah.
You change the blade of the angle or change the shape of the blade. Yeah.
The shape. Yeah.
Okay.
The shape.
Okay. Thank you very much. Yeah. So there's no more questions. So yes, thanks a lot for both the speakers today. Very good, excellent speaking, and thanks a lot attend these meetings. Actually, we have two different platforms. This is the Zoom platform, and we also have WeChat, the platform in another software, so you cannot see it. And most of the Chinese guys and not so many, just several, some of these foreigners have the WeChat, so can see it. So thanks a lot, and this is time to close this IMFTF 30, and welcome everyone to see you in next IMFTF, maybe in next month or in next 2 months. So Kadire, see you in March.
Thank you very much. Thank you. Thanks for organizing this, and thank you, Colin and Nan. Thank you very much. Very interesting.
Bye bye everyone.
Thanks,
bye
everyone.
Bye bye.
Thank you. Bye.